Hi guys, welcome back. So in this video, let's look at what conditional probability is. And we'll also use conditional probability and some of the probability theory that we learned in the previous video to actually see how this can be used in real life in applications such as market basket analysis and recommender systems. Okay. So first off, what is conditional probability? Let's say A and B are two events, all right, that form a sample space. Then the conditional probability that B occurs given A has already occurred is given by this formula P of A and B upon P of A. Okay, this is a conditional probability B occurs that B occurs given A has already occurred. Okay, now so conditional probability and joint probability together are used in something called association rule learning. Now, association rule learning is a learning technique that is used in market basket analysis and recommender systems. What is market basket analysis? Market basket analysis is used to predict products that retailers buy together. Okay. For example, if there's some online grocery shopping website and they have a huge database of all the items and all the items that people usually buy together. So if I buy chips, I'm also more likely to buy some soft drink like Coke or Pepsi, right? That is usually what is seen. And market basket analysis can actually help us find out what those items are that people buy in tandem, and then it can recommend that to us. Then if we know what people buy together, they can be recommended during checkout. That in one of those, did you forget? Do you want this or something? So there was a study conducted in 1998 which showed that people who buy a lot of beer also tend to buy a lot of baby diapers. See, there's no correlation here, but if you use see, there's no correlation here, right? There's no way you can figure out that someone who buys beer might also want baby diapers. But using market basket analysis and some basic probability, we can actually implement this in the system and recommend diapers to the person who's buying beer or beer to the person who's buying diaper, right? So let's understand what association rule learning is. It just basically makes use of joint probability and conditional probability. And with this example, I'll show you how it's used to recommend products to retailers. So joint probability, as we all know, is the probability of A and B upon the total number of observations. And conditional probability is the probability of A and B given the probability of A. Okay. So let's look at this example here. What association rule learning does is that it tries to find an association between different entities in a database. In retail, it helps find an association that exists between different items. What do you mean by association that exists between different items? It basically means that if X and Y are two mutually exclusive sets, in this case, X and Y could be two items like apple and bananas, then what is the probability that if I buy X, which is bananas, then I would also want apples, right? So that is what association rule learning helps us do. So let's look at some measures over here that help us recommend systems. First, there is something called the SKU, which is the stock keeping unit. The stock keeping unit are nothing but all of your items: bananas, peach, plum, strawberry, grapes, orange, apple. These are all your stock keeping units. And these are the transaction IDs. For the sake of simplicity, I've only taken 7 transactions that was done. Let's assume that in our entire store we have only these 7 items, and only 7 people came and bought stuff from us. So what we want to measure the strength of association between two given items. For this example, I'll be trying to establish an association between apples and oranges, right? Sorry, apples and bananas. I'll be trying to establish an association between apples and bananas. So I want to find the strength of the association. So for that, I have some measures. First off, there's a support. The support is nothing but the joint probability between apples and bananas, okay? N of X and Y upon total number of observations. Confidence is nothing but the conditional probability. What is the probability that I'll buy Y given X? Y over here is bananas and X over here is apples. What is the probability that I'll buy bananas given that I've already bought apples? So that is given by P of X and Y whole upon P of X over here. Then there is the lift, which is the P of X and Y, which is basically conditional probability, but also multiplied by the probability of bananas in the denominator. So why is lift good is because it helps us, in the case that where P of X is very, very small, the confidence would not hold much value, right? Because if P of X is very small, this would tend to 1. So lift helps us overcome that. It helps us overcome the fact that that the denominator and the confidence can be very small. And this helps us sort of, take into consideration that P of X is small. So we also use P of Y. So let's try and establish an association between apples and bananas. Okay. Support over here is n of x and y, right? I'll get the table here. So support over here is n of x and y upon total number of n. N of x and y is the places where I have bought my apples and bananas together. So as I can see that there's only one, there are only two, right? Transaction ID 1 and transaction ID 5 are the places where I've bought apples and bananas together upon the total number of observations, which is n. So there are 7 transactions, right, in total. So that's the total number n. So that's 2 by 7. I get the value 0.285. Confidence is the probability that x and y happen together upon the places where x happens. Okay. So x and y, again, as we know, happens. X and y is where I buy apples and banana together. That's again in 2 places, as we saw in support. Now, the denominator here is not the total number of observations, it's the probability of buying apples alone. So we see in all the transactions where I have bought apples, that is just in 3 places, 1, 2, and 3. So the denominator here is 3. This is actually 2 by 7. Just so that you don't get confused, it's 2 by 7 whole upon 3 by 7. Right? And the 7 gets cancelled. This is just so you don't get confused. I wrote it in short. So it's 2 by 3. This comes out to be 0.667. And the lift here is P of x and y, given P of x into P of y. Similarly, using the same methodology that I used for confidence, I calculate all these values. I get 2 by 7, 3 by 7, 6 by 7. P of y is the places where I have bought bananas. Okay, the probability that I will buy a banana. So that's 1, 2, 3, 4, 5, 6. So I get the value of lift as 0.778. So I have my support, I have my confidence, and I have my lift. And using these values as a business, I can set thresholds for the items, right? So I can look, generally these are just 7 items and 7 transactions, but in real life transactions will run into millions. So if I perform a lot of analysis, I can set the thresholds using the measures of support, confidence, and lift. After setting those thresholds, if one of these values crosses the threshold, I can recommend the item together to the retailer, to the person who has bought these items. Okay. So that's what is written over here. Association and business rules about who buys what in tandem together can be generated for using thresholds like this one. Okay, this is just an example. So this is how I want to show you how simple probability can be used in real life, in real world analytics applications like recommending items for retail users, for retail buyers. Okay. So now before I move on to the next video, which is Bayes' theorem, I just want to, just for the sake of it, I want to establish the difference between independent events and mutually exclusive events. People tend to get confused in this. I just want to clear this out. Mathematically, independent events are P of B given A is equal to P of B, and P of A given B is equal to P of A. This means that the event B is not at all affected by the occurrence of A, or the event A is not at all affected by the occurrence of B. Let's take an example that we are throwing. The example is that we are throwing two different dice together. Okay, now dice one, we want to find the probability of getting 6 in a throw, and for dice two, we want to find the probability of getting 3 in a row. Now, obviously, if I'm throwing them together, the fact that I get a 6 on the first die has nothing to do with what number I get on the second die, right? Which shows that these are independent events. Okay, so if I want to calculate the probability for this would be basically P of D1 into P of D2, right? Taking in terms the mathematical notation I've written over here, this would be P of B into P of A. That is what independent events are. Independent events can also come from different sample spaces. Okay, let's go on to mutually exclusive events. Mutually exclusive events basically says that P of A and B, P of A given B is equal to P of B given A is equal to 0. Now P of A and B is P of A given B is basically P of A and B, and P of B given A is equal to P of A and B upon P of A. This is P of A and B upon P of B, probability of the event B. So if this is equal to 0, this can only mean that P of A and B is equal to 0, right? Because, and if P of A and B is equal to P of A, if it's the same thing, then this means that my sets are totally different, they're disjoint. Okay, now the thing with mutually exclusive events is that they can also come from the same sample space. Suppose, for an example, let's take die one is let's take two events where I throw only one die. Okay, one after another. The first is getting a 6 on the first row, and the second is getting a 3 on the second row. Now, on the second throw, sorry. Now, P of D1 and D2 is 0, right? Because me getting a 6 on the first row has nothing to do with getting a 3 on the second row, and I'm throwing only one die here. So this is what you call mutually exclusive events. So I'll stop the video here, and the next video we'll go on to the Bayes theorem.